Okay, so welcome everybody. We will proceed with the defense of the thesis from Paolo Sebastiano Flores. We will have a presentation of around 45 minutes, and we will follow with the questions from all the members of the panel. So please, Paolo, you can start.
Okay, so thank you all for being here. Yes.
No, try. Forward. Try now.
Let's try now. Prova? Better? Okay.
Alexander, he can hear you well, please.
I can hear. I can hear.
Can you hear me well, Professor? Yeah, you can. Perfect. Okay, so thank you all for being here. Welcome to my thesis defense titled Interplay between Doping, Thermal Properties, and Morphology in Organic Semiconducting Polymers. Let's start with an introduction and a little bit of context on the topic. I think there's still a little bit of feedback, but maybe.
Let's look for assistance. I don't know how it works.
Okay, so the thesis focus will be on the simulation of organic semiconductors, and particularly with a focus on their applications in thermoelectrics. We will make use of molecular dynamics for the calculation of thermal conductivity and density functional theory for the study of doping. So the thermoelectric effect, as we all know, is the conversion of a temperature gradient, delta T, into electric voltage, delta V. And it's governed, the main parameter governing this effect is called Seebeck coefficient, and it's defined with the very simple formula. In order to measure the conversion efficiency, we can define the dimensionless figure of merit, ZT, which is defined as the ratio between the electric conductivity sigma times the Seebeck coefficient squared and divided by the thermal conductivity kappa times the operational temperature T. Therefore, a good thermoelectric generator must exhibit a large S and sigma and a low kappa. When we look at the state of the art, inorganic thermoelectrics show values of ZT, the best one that we know of, until now, around 2.4, 2.5, 2.6 at various operational temperatures, and they are made of elements such as bismuth, telluride, antimony, tin, and selenide. Whereas organic thermoelectrics usually employ organic semiconductors, and one of the best we know of is P.PSS in a solution, which shows a significantly lower ZT at the moment of 0.42. Just to show you the chemical structures of P. and PSS. So you might think, well, let's go with inorganic thermoelectrics, right? It's much more efficient. But, well, as a matter of fact, inorganic thermoelectrics are made of usually toxic elements, rare elements, and it's quite expensive to fabricate. Whereas organic thermoelectrics are mostly non-toxic, biocompatible, earth-abundant, and cheap. And so made of earth-abundant elements, and therefore inherently cheap. And so it makes sense for us, despite the gap in performance, to pursue this road. When we talk about organic semiconductors, we need to talk about doping if we want to achieve high electrical conductivity. So p-type doping occurs when the when the lowest unoccupied molecular orbital, or LUMO, of the dopant is lower than the highest occupied molecular orbital, or HOMO, of the organic semiconductors, as is depicted here. On the other hand, N-type doping occurs when the HOMO of the dopant is higher than the LUMO of the organic semiconductor. When we dope, we are introducing charges, of course, in the semiconductors, and these charges also are associated to distortions in the polymer structures called polarons or bipolarons. Polarons have unitary charge and spin 1/2, and polarons form when two polarons come together by overcoming their Coulomb repulsion barrier, when the energy gain from the structural reorganization is higher than this repulsion, than the Coulomb repulsions, and they have spin 0 and charge plus or minus 2. So organic semiconductors undergo an aromatic to quinoid transition upon doping, which means that an inversion of the bond length alternation occurs, which means single bonds become double and vice versa. And they also experience increased stiffness or rigidity in the polymer chain. There are several doping approaches, such as molecular doping, electrochemical doping, ion exchange doping, but we won't get into much detail with this. What we will get into detail is with Lewis pair doping later. So how does doping affect the thermoelectric efficiency of organic thermoelectrics? Let's talk about first doping and power factor. So power factor is sigma times Seebeck coefficient squared, and is the numerator of the dimensionless figure of merit. Despite the formula here, it has been found to increase empirically with the square root of the electrical conductivity, which you can see here in this nice graph from Mariano there, from a focus article of Mariano. Thank you. And if we recall, the electrical conductivity is nothing but the product of charge carrier density, elementary charge, and mobility mu. But the Seebeck coefficient is inversely proportional to the charge carrier density n. Therefore, we have no other choice than to improve mobility in this expression here to improve the power factor. And how do we improve mobility? For example, we know that excess dopants reduce the mobility by altering the density of states. Therefore, we need to achieve maximum electrical conductivity while minimizing dopant concentration. Moving to the effect of doping on thermal conductivity, we know that the total thermal conductivity of any material can be expressed as the sum of an electronic component kappa E and a lattice component kappa L. Kappa E, so the electronic component, is related to the electrical conductivity through the Wiedemann-Franz law, where this factor L is called Lorentz factor. The Lorentz factor is usually assumed to take on the Sommerfeld value, which is the maximum theoretical value, and which has this expression. However, this does not hold for a large range of organic semiconductor. It does hold for inorganic and metals usually, but it doesn't hold for organic. And there are several things to note. Thanks again, Mariano, for this graph from your focus article. So increasing sigma will eventually destroy the thermoelectric efficiency due to this increase in the electronic component of kappa. Yes, which we can see in the graph. Actually, there's a maximum. When we increase too much the electrical conductivity, the thermoelectric efficiency starts going down. And the other thing to note is that reducing the lattice component of kappa shifts the maximum efficiency to lower electrical conductivity. And this means that by reducing the requirements of electrical conductivity, we can use less dopants. We can also improve the mobility. We can improve the power factor. And overall, we can improve the thermoelectric efficiency just by reducing the kappa L. Let's move to some theoretical background on molecular dynamics. So molecular dynamics is a computational technique based on classical statistical mechanics, where particles are treated as classical. Therefore, in order to calculate the trajectories of the atoms, we need to solve Newton's equations of motion. And we can calculate the force on each particle by calculating the negative gradient of a certain empirical potential that we call U. And we need to choose a functional form for U, which is called force field. And this empirical potential, it can be divided into a set of bonded terms and so-called bonded terms and non-bonded terms. For example, the general amber force field, or GAF, is one of the most popular, and it takes these expressions for bonded and non-bonded, and where we have here terms representing the bond stretching, angle torsion, dihedral torsion, and dispersion forces with the Lennard-Jones potentials, and Coulomb potential for electrostatic forces. So we have introduced a little bit of molecular dynamics, and to calculate the lattice thermal conductivity, or kappa L, we use a molecular dynamics technique called approach to equilibrium. It works like this. We define two regions in the sample and impose a step-like temperature profile, as you can see here in the picture. We define T1, for example, greater than T2. So we have a hot region of the sample and a cold region of the sample. Once we have this step-like temperature profile, we let the system reach thermal equilibrium again in the microcanonical ensemble, or MVE. While we do this, we monitor the average delta T between the two regions here. And this delta T will, of course, decay to zero, and it will do so in an exponential fashion. And from this exponential decay, we can easily extrapolate the kappa L. Basically, the faster the delta T decays to zero, the more conductive the sample is. We have implemented this with the LAMPS software suite. Now that we have introduced a bit of context and theoretical background, we can talk about the results on P-dot thermal conductivity. So we have chosen this system because of its promising performance, and we wanted to know how does doping affect, how does doping and chain length distribution and counter-ion type affect kappa L in this system. So we have used the approach to equilibrium method for the calculation of KL, and we have used a P-dot specific force field that has the same functional form as GAF, that is trained on DFT, P-dot DFT data that is available in the literature. It is available for both its doped and undoped state. and it's specifically developed to account for the aromatic to quinoid transition. So we have used the molecules depicted in this picture. We have a p dot chains of 6 monomers, 12 monomers, and 18 monomers, so different chain lengths, and one long PSS molecules of 50 monomers. These are the molecules that we have used. To generate the sample, we define a cubic simulation box and just randomly insert the molecules. And we need to differentiate between two cases. One case only contains p dot molecules and no PSS. And in this case, we have run in the isothermal isobaric ensemble at 300 Kelvin and 1 atmosphere with a time step of 0.5 femtoseconds for a total simulation time of 10 nanoseconds. In the case of p dot with PSS, we have on top of this protocol here, we have also added annealing cycles at 1100 Kelvin. So of course, for pristine p dot, we have simulated them both in the undoped and in doped state to create a baseline and then to see how doping affects the thermal conductivity. So this is a summary of the samples that were created. And you can see here the various chain length distributions. So for example, the first line refers to samples that only contain chains of 6 monomers. The second line only contains chains of 12 monomers, and so on. And here, the average chain length is summarized. So we have 6, 12, and 18 in these 3 cases, and somewhere in between 6 and 12 monomer units of average chain length for the other samples. Sorry, one more thing. The doped p dot samples, of course, they bear a positive charge, and it needs to be counterbalanced by chlorine anions to preserve charge neutrality in the box. There is only one p dot with the p dot PSS samples with this chain length distribution and 180 PSS molecules. And we have also created a sample which only contains PSS with its negative charge balanced by sodium cations with no p dot, so 0, 0, 0. This is how a p dot PSS sample looks. On the left, top left, you can see the p dot molecules. On the right, PSS molecules, and here on the bottom altogether. All of the samples contain approximately 240,000 atoms. Moving to the results. So let's look at undoped p dot first, so which means the blue lines. What we see is a positive correlation between kappa L and the average chain length. This is a very well-known behavior in polymers in general, which we expect to see since when we increase the average chain length, we increase the covalent bonds within the chain, and this favors intra-chain transport, and this results in an overall increased thermal transport. When we look at the density in the samples, there is no clear trend, but there is some sort of a weak negative correlation between density and average chain length. When we look at the doped p dot, so the red line, we see that the red line is generally above the blue line, so there's a general increase of kappa L. However, the value for 6 monomers and for 18 monomers are the same, and there is actually a sort of maximum here in between around 9 and 12 monomer units. On the other hand, we see a stronger negative correlation between the density the density of the doped samples and the average chain length. So you see here that it's steadily decreasing with average chain length. We attribute this directly to the aromatic to quinoid transition. And this is because there are two competing phenomena here. So kappa L wants to increase because we are increasing the average chain length, but at the same time, the density is also decreasing. Why? Because the quinoid structure that is associated with P dot, with doped P dot, is much more stiff and rigid, and therefore it creates sort of empty spots in the sample where the interchain transport is hindered, and this is much more evident when we increase the length of the P dot chains. And yes, so it results in this behavior which is different from the neutral case. It's not just monotonically increasing. On the other hand, when we add PSS to the sample, we see a sharp increase in KL. So the sample with PSS is this green triangle here, which is much higher KL, and this is only due to PSS itself, since it has a higher thermal conductivity and it increases the overall thermal conductivity. You could say that maybe PSS is just changing the morphology of P dot, and you would have a point. But we also calculated the thermal conductivity of PSS alone, and this is much higher than all of these values. This is 0.25, and this is right above here, which we cannot see. Let me introduce, before going further, the principles of X-ray diffraction. So this is a technique to characterize the crystalline structure of materials. This is based on Bragg's law here, and you see it depicted in this figure. And what we need to do is basically solve this Debye scattering equation, which gives us the intensity of the diffracted X-rays, the pattern as a function of Q, which is reciprocal space. And based on this pattern, we are able to just calculate with a very simple formula the crystal plane spacing of materials in order to simulate this technique. We have used software called Debye, which is available on GitHub. So we have used this software to generate these patterns, and we see that on top we have the P dot undoped samples, and on the bottom we have the doped samples. So this peak right here corresponds to a pi distance of 4 angstroms, whereas down here it has shifted to the right, which means that corresponds to a pi distance of 3.6 angstrom. So we can conclude that doping is responsible for a pi distance reduction from 4 to 3.6 angstrom. This does not appear to have any implication for thermal conductivity, but it probably does for electrical conductivity, since reduced pi distance also means increased tunneling probability. We have also defined a custom measure that we called local crystallinity measurement, where basically we assign a vector S to each monomer along the backbone direction, and they are depicted here. So the black dotted lines are P dot chains, and so each dot represents a monomer, and if you follow the dots, you see how the P dot chains are conformed here in the sample. And what we do is we calculate the dot product within a certain radius with the following formula. And we assign a value to each point in a grid that we define in the sample. And we are able to just graph a color map when we can see the points in the sample where the chains are most aligned, since the dot product will be maximum where the chains are aligned. Yes, so once we've introduced this, we see that we have also calculated the simulated X-ray diffraction patterns for P dot PSS. And there's a 3.5 angstrom P dot peak here, and here for PSS benzene pi distance of 5.2 angstroms, which is in agreement with the literature. And we have also used the local crystallinity custom measurement, where we can see that there are small P dot aggregates. You see the blue spots mostly. That's where the P dot chains are, approximately of diameter of 2 nanometers. We have also studied a different arrangement of P dot, which we call P dot crystalline nanofibers. We have followed a very different protocol to generate these samples. So you can see it in the scheme here. So we take one chain and we just replicate it in the space in all the 3 directions of space, pi stacking, lamellar, and backbone, and until we have something that looks like this in panel B. So very different from what we saw before. And we have to differentiate between 2 cases here as well. The 2 cases are depicted in panel C here and panel D. So the first case in panel C represents samples which contain some van der Waals gaps here in the middle, whereas in panel D here, the simulation box is wrapped around one single chain along the backbone. And so there are no van der Waals gaps. Why do we do this? Because when we apply the approach to equilibrium technique, we define half of the simulation box will be right here or right here. And this is very different because in this case, the heat will need to jump from chain to chain, whereas here, it will not need to jump from chain to chain. So we are basically separating interchain and intrachain transport. We, of course, expect this system to have anisotropic transport properties since the transport mechanisms along the different directions are very different. And we want to know if we could leverage this anisotropy to suppress kappa L. This is a summary of the samples that we created, also in this case with P dot chains of 6 monomers, where you can see the number of replications in the space, number of replications along the backbone, along the lamellar, and pi direction. Same things for P dot chains of 12 monomers and P dot chains of 18 monomers. Moving to the results, let's first discuss 6 monomer P dot chains here. So when we look at the lattice thermal conductivity along the backbone here, we can see that it's increasing as a function of the length of the nanofiber. Why? This is an artifact of molecular dynamics techniques because basically what we are seeing is that the boundary scattering is prevalent in the sample, but when we increase When we increase the length of the nanofiber, we see that the boundary scattering will become less and less relevant. And so the first thing to say is that the backbone conductivity is not the most conductive direction. In fact, we have here 0.2 watts per meter Kelvin, which is very similar to the lamellar value. And this was surprising, since we expected the backbone to always be more conductive, but it is not the case. So it appears the interchain transport from chain to chain is limiting the conductivity. On the other hand, something that we expected was that the pi-pi direction is the least conductive. Similar things can be said, the same things can be said for pitot chains of 12 monomers. Yes, I forgot to mention, so you see I put two arrows here, type 1 and type 2. So this refers to how the nanofibers can arrange along the backbone. So we see type 1, we refer to H bonds between dioxyethylene groups of the terminal monomers of different chains. And you see there's this sort of S behavior. Whereas type 2 is a little bit different, and it's an oxygen-sulfur electrostatic interaction, also between terminal monomers of different chains. And we do not know, we couldn't reliably recreate, like define a protocol to generate either type 1 or type 2 lateral registry. This appears to be just a chaotic phenomenon, and it depends on heavily depends on the initial positions of the atoms when we do the replication. And it appears that type 2 produces higher thermal conductivity. We can also see that here, where type 2 is slightly higher than type 1. And in the case of 18 monomers, pitot chains made of 18 monomers, the backbone appears to be now more conductive, since we are here at 0.4, which means that intrachain transport becomes more relevant for this chain length. Similar things can also be said for lamellar and pi-pi direction, as the previous cases of 6 and 12 monomer chains. Now moving to the pitot samples that do not include van der Waals gaps along the backbone, we created them with chain lengths of pitot ranging from 6 to 36. So there is only one repetition along the backbone, and increasing numbers for lamellar and pi-pi. So what you see in this graph is the inverse of the thermal conductivity as a function of the inverse of the backbone length of the nanofibers. What we can do with this is the blue line, the blue dots here, we can fit them in a straight line, and the intercept with the y-axis will give us the inverse of the lattice thermal conductivity as a limit case, which means for infinite pitot chain length. And so we calculated this, and it gives 2 watts per meter Kelvin. We do this fitting to basically to single out the effect of boundary scattering. And we did similar things for pitot chains of 6 monomers, and it gives 1 watt per meter Kelvin. So now let us introduce a little bit of density functional theory. So DFT is a computational technique used to investigate the electronic structure of atoms and molecules. And it's basically what we want to do is we want to solve the Schrödinger equation, which takes this general form. But this is an incredibly complex task, unless we're talking about a hydrogen atom, for example, hydrogen molecule, unless we start taking some approximation. For example, the Born-Oppenheimer approximation is we consider the nuclei as fixed with respect to the electrons, which makes sense since nuclei are much bigger and much heavier and much slower than electrons. And this allows us to divide this Schrödinger equation into an electronic and a nuclear equation. The electronic equation looks like this, and the nuclear equation looks like that. Once we are able to solve the electronic part, then we can plug it in the nuclear equation and we can solve the entire problem. However, the electronic equation is still quite complicated to solve, and we need to take more approximation. And here comes the DFT, which is supported by the Hohenberg-Kohn theorems. First theorem says that the Hamiltonian for the electrons can be retrieved by finding the ground state electron density ρ. And second theorem states that ρ can be found by minimizing a certain energy functional E of ρ. So yes, what we need to do is we need to find a satisfactory functional form for this energy functional. And then we can find the ground state electron density. With the ground state electron density, we can retrieve the Hamiltonian for the electrons. With that, we can solve the electronic Schrödinger equation. And with that, we can solve the nuclear one. And we have solved the entire problem. Having introduced this, we can start talking about our research topic on doping of organic semiconductors. So this was a nice paper that I was able to collaborate, in which I was able to collaborate with Mariano, which invited me and Ricardo to contribute. So Lewis pair dopant complexes. Okay, Lewis pair doping is a solution-based doping method where we use a Lewis base and a Lewis acid in conjunction. And what happens is that the base uses its lone pair to create a coordinate bond with the acid, forming a Lewis pair. In the case of these two molecules, which we call BCF and F40CNQ, what happens is that the cyano groups here, these four cyano groups in the F40CNQ, they are able to form a Lewis pair with the boron atoms in BCF, this one. When this happens, the cyano groups then become electron deficient here. Therefore, the pi orbitals from the backbone of F40CNQ are attracted to the cyano groups, which in turn leaves the backbone electron deficient, which deepens the LUMO. And if we recall p-doping from the previous slides, deepening the LUMO means that now we are able to efficiently dope, to efficiently p-dope up to much lower values of HOMO, of any organic semiconductors. For example, P3HT has -5 here, and F40CNQ and BCF individually have -5.2, -5.3, but when we use them with the Lewis pair doping approach, we are able to go down up to -6.1. This also leads to improved thermal stability, which we can see in the graph here. So these represents sequential annealing cycles applied to a P3HT film. where we see that when we dope individually, either with BCF of F40CnQ, the electrical conductivity just plummets down where, after a few annealing cycles, whereas when we use the Lewis pair doping approach, it only starts decreasing after a much higher temperature of annealing. So my contribution to this study was minor. We performed DFT calculations to see how the F40CnQ and BCF complex forms, and also to estimate the binding energy of this complex and its bonding distance. So this is what we found. Actually, we found two different geometries, configurations, one in A and one in B, but this one is B is actually very unstable since binding energy is minus 11 millielectron volts. The one that we are interested in is this one, and it gives minus 0.24 electron volts and a distance of approximately 1.6 angstrom. The high energy binding energy that we found is consistent with the increased thermal stability. We also performed another study, this time on an N-type organic semiconductor called PBFDO, which is depicted here, or polybenzofurandadione. This is a sidechain-free N-type polymer. In the literature, it has been found to have a doping efficiency of up to 86%, so almost 9 electrons per 10 monomers, an exceptionally high electrical conductivity of around 2000 Siemens per centimeter, and fairly good thermoelectric performance. So therefore, we decided to study this polymer since it also has, it's also very promising. And we wanted to see if there is a way to optimize the doping efficiency without using more dopants. So and before moving on, let me introduce this method called cluster continuum model. This is a computational model for the calculation of solvation-free energy of ions in solution. In our case, we will deal with protons in solutions. So, yes, how this works is that we treat short-range interaction quantum mechanically. So anything that is in white here, we treat quantum mechanically. The proton in a gas phase and the N molecules of solvent, and also the interactions between the proton and N molecules of solvent, we treat quantum mechanically. Everything else, so the rest of this solvent outside of the solute cavity here, is treated as a dielectric continuum. This allows us to reduce the computational complexity while still obtaining reliable values for the Gibbs free energy of solvation. So the doping reaction of this polymer is looks like this. So we add durohydroquinone, or TMQH, to the polymer, and we obtain durohydroquinone becomes duroquinone and releases protons, and the polymer is doped. It has received 2 electrons from each molecule of dopant. So we see that we have some protons here in the gas phase, and we actually need to take account of that using the cluster continuum model. So we need to take into account N molecules of solvent explicitly, which allows us to calculate now the actual delta G of the doping reaction. And in our case, it looks like this, where I have rearranged a little bit the terms in order to include the delta G of solvation here. Why did I do this? Because it turns out delta G of solvation is is really important in this reaction, because if we look at panel F here, we see that delta G observation is decreasing with decreasing temperature. As a result of this, the whole doping reaction is favored at low temperature as a result. You can see that the total delta G in this panel A, B, and C for different chain lengths of the polymer. So 8, 6, and 4. So we see that delta G is negative only for of doping concentrations lower than 50%. In this case, also for 66% for temperatures lower than 350 Kelvin. And two things to note. So in panel D, we see the delta G of reaction for a PBFDO chain of 8 monomers, of 4 monomers, and of 8 monomers below. So the first thing to say is here that these are both at doping concentration of 50%. And of course, the longer chain of 8 monomers has a much negative delta G. This is to be expected since when we increase the chain length, we are also increasing the conjugation length, which means reducing the band gap and making it easier for the polymer to be doped. Second thing to note is that when we look at delta G as a function of doping concentration, we see a steady increase for concentrations up to 75, 80%. And then there is an abrupt increase for concentrations higher than that. These two things together lead us to expect that the delta G zero crossing for longer chains might be expected to occur at higher concentration. By zero crossing, I mean the value of the concentration here for which the delta G becomes positive. These two things together might explain, yes, how in the literature a doping efficiency, an experimental doping efficiency of 86% was obtained with long chains despite conducting the reaction at high temperature. So to give a summary, we have investigated amorphous PDSS, and we have assessed the impact of doping on the lattice K, where doping generally increases kappa L, but interchain transport is hindered for long chains due to increased stiffness associated with the quinoid structure. We have also found out that PSS itself, when we add PSS itself to the mixture, this is the factor that contributes the most to the increase of kappa L. We have also talked about p-dot crystalline nanofibers. We have seen that thermal anisotropy can be leveraged to a certain extent to suppress kappa L if we are able to control the size and the aspect ratio of the p-dot nanofibers. We have tried to explain the mechanism of BCF-F40CNQ complex formation and the Lewis pair doping approach. And we have estimated its binding energy and bonding distance. We have also talked about how to optimize the doping reaction for PBFDO. We have found out that it is favored at low temperature, and that these findings suggest that the impact of temperature synthesis should be experimentally tested, since lower temperature could boost doping efficiency without using more dopants. So I would like to acknowledge ICMAB-CSIC and Universitat Autónoma de Barcelona, where I conducted my PhD. I'd like to thank Horates and the European Union, which financed my research, and TESGA, Galicia Supercomputing Center, where I performed all of my calculations, as well as Linköping University, Chalmers University of Technology, and Hot Disk, where I where I was hosted for secondments in Sweden. I would like to say thanks to Riccardo, my supervisor, to Mariano, and Sebastian, and Anna La Romain, and my former professor in Sardinia, Claudio Melis, Igor also, and Bechira and Christian, who hosted me in Sweden, Doro, who was really important for the Horates project, and all of my ICMAB and Horates colleagues. So thank you very much for your attention, and I'm ready for your for questions.
Okay, thank you. We will proceed now with the questions. First of all, let me introduce the panel. We have, yeah, maybe if you stop sharing the presentation so we see Alessandro. Okay, so let me introduce the panel in first place. We have Dr. Alessandro Troisi online. We have also Jordi Faraudo here and myself, Marta González. And we will do as following. Each of us will have half an hour for questions, and we'll start with Alessandro. So please.
Thank you, Paolo, for your presentation. It was very clear. Thank you for your work. It was very interesting to read. I know that the setup is not ideal with your camera and my face pointing in different ways. So please do answer in the way you feel more comfortable. I can hear you very well. So if you want to face the audience, it's fine. Yeah, whichever way works for you will be fine.
A little bit halfway.
Really, and then yeah, don't be just relax about that. Don't worry. So as a part of this experience as a doctoral student, you have become now an expert in simulating heat transport in polymer. So I almost have only one question, but I like to break it up in a small one. I really would like to know what can go wrong in this simulation. What are the things we need to pay attention to? So I like to unpick various decisions you've taken as you run the simulation to see what is the learning experience and what we know now that we didn't know before you started your project. So I have like a list of sub-questions, but ultimately it's mostly about what do you know now? So imagine that someone knows everything about molecular dynamics, they've done the module, they apply something else. So they want to know what's different once you do heat transport. And so let's start with the force field, for example. So we'll consider the other. I see a generic introduction in chapter 1 about GAF, but can you tell me more? Do we need to pay special attention to the force field when we want to study heat transport? So what is different than the application not in this area, specifically regarding the force field?
Yeah, so let me go back maybe. I know. Just a second. Well, maybe I don't need it so much. Anyway, so what's different? So basically, I would answer by telling you how we landed on that specific force field. It was so before starting my PhD here. Well, it's not important. So before starting my PhD here, I was studying at the University of Cagliari with Professor Melis, and he was kind enough to send me to California, to Stanford University, where some very much more proficient than me scientists, much more experienced and proficient than me, they were at the time working on this PDOT specific force field that I ended up using. So I saw firsthand how they were developing that force field, and what they were doing was basically lurking in the scientific literature on PDOT to find whatever they could find, like data on geometries, vibrational energies, and torsional potentials, and all of this stuff. And they were compiling that together and developing a force field based on those data. And what they did when they had the force field, they made a comparison for several properties of PDOT. So they used GAF as a baseline, and they used their own force field to compare it with. And it turned out that their force field, of course, since it's much more specific to that system, performs much better in terms of specifically thermal properties, but also some mechanical properties such as the word is escaping me now, the persistent length and others. And so since I had this available, it was an obvious choice for me to use that force field. And yeah, it really changes the results.
So maybe to refocus the answer, this it was interesting to hear. But now, suppose you have another polymer that you want to study, for which you don't have a friend who has worked so many. So what are the things we need to pay attention to? Because of course, maybe there are something we don't care, something is very important. So what are the features we should pay attention to, or can we just use GAF out of the box and so on?
I think to start with, if you don't have this option like I did, yeah, GAF is perfectly fine. And then if you really need to, then maybe you can start thinking about creating another more specific force field. But the thing that without this option, the thing you must take more into account, I think, is you need to try out different protocols for generating the samples and see what suits you the best. For example, I have to say, I was trying several things. For example, with the amorphous P.PSS, which didn't work out, and I was getting some morphologies that just weren't right. Until actually I have to say thank you to you as well, because you published a paper with with a protocol for that, and I was able to just copy it basically, and it worked fantastically. And it actually changed the results a lot from what I was seeing before, and I had to change completely all of the conclusions I was coming to. So back then, when I wasn't so expert on this, I didn't know that, and then now I know.
So last question about the force field, because essentially your answer could apply to any specific application. So if I was asking about the force field for protein, a force field for silica, you will say more or less the same. Let's start with the routine, unless we have more time and we develop it better. But maybe now that you have specific application, now thermal conductivity is kind of specific, like maybe 0.1% of all people doing MD do thermal conductivity. So is there any part of this force field? So we know you show in the presentation what it's made of, intramolecular, intermolecular bonding, and so on, charges. Is there any part of this force field which you think is particularly critical for thermal transport?
I think so, yes. These researchers in Stanford, they did not change The only thing that they didn't change, I think, was the van der Waals parameter. So that is not important, I guess. The most important thing was the dihedral parameters. So the one that refer to 4 atoms, the torsion between planes defined by 4 atoms.
Okay, I'll stop you there for a moment because maybe in a later question it will be more relevant. But then these are features which affect property they've looked at, like X-ray, the crystallography of this polymer, or persistent length, but nothing specifically for thermal transport. Is it right, or they look at thermal transport themselves?
No, they looked specifically at, well, one of the things they looked was thermal transport. So they calculated the vibrational spectra and they fitted the force field to reproduce the vibrational spectrum of P dot.
Okay, so yeah, that's a good point to leave this conversation for a second, and then we'll come back to vibrational spectra a bit later. Then there is the force field. Okay, complicated, attention to everything, including the vibrational pattern. Now, molecular dynamics part. So I'm specifically referring now to this 2 temperature but that you have. So there is only a figure in the thesis, not really. I don't think we need to go there because yeah, I have the thesis in front of me, and really the details is not there. In fact, I'm going to ask about a detail that is not present. So what should we? What are the parameters of your simulation? So what can go wrong when you do these things? So there will be decision about the size, the difference in temperature, the fitting. So can you tell me a little bit more? What is the success rate of this approach, or what you should pay attention to?
Yes. So right, I didn't say. So in my case, T1 and T2, they were always 400 Kelvin and 200 Kelvin. So this delta T was 200 Kelvin, right? What can go wrong? What sometimes went wrong was that this delta T would go to 0, but then the total temperature would not be 300 Kelvin, which should be, it should be perfectly in the middle between 400 and 200, but sometimes it didn't. And this fact actually told me that then the sample I was simulating was not really relaxed, was not in its most stable point. And so then I would need to work more on the protocol of relaxation, of generation of the sample. For example, this was something that usually went wrong, and then I would have to work more and then repeat it again and again. Also, something I didn't say is that for each sample, I do this in all 3 directions of space, and the values that you saw are an average of that.
So have you checked for effect of the delta T? So maybe instead of 100 Kelvin, 200 or 50, and also effect of the thermostat, because of course now there is a magic object in your simulation which is fixing the temperature, and then it can do a good job or a bad job. So have you modified these parameters?
The thermostat. No.
And the delta T.
The delta T, yes. I tried to modify it to make it smaller, but yeah, it didn't really change things. It just, when I would reduce delta T, I would see that then this effect of the temperature shifting would become sort of less visible, but still there. So yes, it didn't solve the problem.
Yeah, so let's explore this a bit more, because what you say, you can imagine it. If you put delta T 1000, you see a big effect and you have problem. If you put it 2 Kelvin, you see a smaller effect, and I would imagine you have a less theoretical problem, because of course now you are in quasi-equilibrium and so on. So now there is a trade-off between, so what is the trade-off here? So why don't we make the temperature larger? Why don't we make it smaller, essentially?
So the let's say the midpoint between T1 and T2 needed, well, I wanted it to be 300 Kelvin, so room temperature. So I had to go from there. So actually I couldn't go more than 600, I guess. Since I couldn't go lower than 0. So second thing, when delta T is too small, then actually what I'm doing is that what will happen is that I will have a lot of noise in the data.
Okay.
And so the
So that
extrapolation will not be so great.
And then when it's too large, what is the problem?
When it's too large, the problem is that then this region, the hot region here, will be molten P dot, and this will be frozen P dot, and so it doesn't really make sense.
Okay,
yes.
so you have a different phase than the one you want to study. So what is the criterion to determine that your temperature is not too high? In the low, of course, is fine. What is your monitoring to say, okay, now I've not created a different material at high temperature, it's more or less the same as at 300 Kelvin. What is the?
I checked that, well, I checked in the literature what's the fusion temperature and the freezing point of P dot. Actually, I couldn't find a freezing point, but yeah, I think the fusion temperature is higher than 400 Kelvin. And I had to imagine that 200 Kelvin is above the freezing point.
The reason I ask about this is because I'm sure you also have this observation. You didn't say during the presentation, but it's fine. When you showed the thermal conductivity as a function of the length, you don't need to show them because you see that there is some noise in the point. So you saw a trend, but also there is a little bit of mess in the middle, things moving up and down and so on. So I wonder if you did any attempt to estimate the error bar of your simulation so that we really decide what is a trend, what is nothing, and so on. And this is related to maybe the selection of delta T, make it very, very small, maybe big noise, but a big error, very large, it's a wrong number. So yeah, it's all connected to the error bar of the simulation.
Yeah, the error bar, I didn't include it because they are very small actually, and for a graphical reason that it would just, I think it would have been a nuisance in the graph.
No, but then yeah, it means that what really means is that you are not computing it well, meaning you are underestimating your error, because I'm sure you don't believe that changing the length from 7 to 8 you have these big jumps, right? So that's another error.
No.
Yeah. So very likely you measured the error bar maybe from the. Also, how did you measure it? And then what could be a good way of measuring? Suppose now we have more time, we want to really get this error bar right, because for example, one interesting thing you mentioned, there is an optimum there is a maximum, okay? So this is a very fundamental finding. We don't expect it. We want to see if there is really a maximum, while now there is maybe a maximum, but then there is a dip and so on. So what could be a strategy to reduce this error bar? And you also mean you need to compute them better because they are not smaller than the point. So
each point here is an average of 3 values, right? So these 3 values are the 3 directions in space. So of course, a good idea to reduce the error bar would be just to perform more calculations, create more samples, and then more and more and more calculations, of course. Well, you're right, probably that we should have done more. However, these are a lot of calculations with a lot of atoms. Yes, I know my supervisor always tells me, drawing it's too complicated because it's too much calculations is not a good excuse. But this is what basically happened here. These are a lot of calculations with a lot of trial and error also. But yes, you would be right that. But I mean, I'm confident we would see this trend.
Okay, but then I can say, let's say that we have no more computer time and we have these points. What's the error bar here? I think there is enough information to say something about that.
Yeah, I mean, it's really small. Like, since this is an amorphous system, all of this, I mean, all of the average value corresponding to one single points are here close by. I think there would be something like probably below 5% standard deviation.
What you say is not really consistent with this plot, right? But if you say it is 5%, it really means that this small change in technology will be measurable. So people make a polymer of length 7, make a polymer of length 8, and get completely different result. I don't believe it. Also, you don't believe it, by the way. So so it means that the error bar that you are obtaining by doing the average is underestimated. And then, of course, if you repeat it many times, start the simulation from scratch, do it 10 times, you get a smaller error bar that will average out, but that's too expensive. And so let's not do it because, of course, we don't want to waste time. But then given this trend, you have now a feeling of what the error bar can be, because you may make assumption that the curve will have at most one maximum, for example, or is at least monotonous, so it doesn't really go up and down that quick. So can you, looking at this figure, estimate now what do you think is a better error bar?
I don't know. Are you asking for an actual range?
Because I don't like that you have connected this point as if there is like a real up and down. So instead of creating a line which goes across them, and then of course
the fitting.
Yeah. But then you can tell me, no, really, this is going up and down. You need to believe me, and you convince me. That's fine. So essentially, what I'm saying is,
No, I don't think it's going up and down. Really. Yeah. This should be monotonous. Yes.
Okay, and so that this implies that if you create a fitting, linear, polynomial, something that goes around that, then you have at least a root mean square deviation, and this will give you a better estimate of the error bar, which is not that the standard deviation of the 3 direction that you measure, let's say. So this is this will help you in your discussion. Otherwise, when you give this presentation, and you say, oh, there is a maximum there. So which one? I mean, so many maxima. While so this is this story is and don't it's very fine to say that you cannot do more simulation. This is the maximum. I'm finishing. Goodbye. That's my thesis. But then the meaning of the number should be slightly clearer. Okay, we've done now the MD things and the sorry, I have to ask this. When we read about thermal transport and you look at the equation, most of this theory has been developed for inorganic crystals. And then you read the books and maybe nothing of them is applicable. You notice that some laws are not true and so on. But then in the theory, all theories, there is H bar appearing here and there, meaning that the vibration are have a quantum mechanical feature, and some of them are very high frequency, and so they're not really cannot really be described using classical mechanics. So, what is the impact of using classical mechanics to study transport? You think for this class of materials?
Well, I think I think there's a study from Professor Melis actually, where I think he calculated the vibrational spectrum of like the phonon spectrum, and it shows that like the huge majority of frequencies are described by molecular dynamics. So I don't think it's. I think what we are getting is a pretty reasonable estimate.
Vibration are described by correctly, let's say correctly, with the same frequency, they're the same frequency. So if a frequency is 1500, 1500 wave numbers, the carbon-carbon stretching, with classical mechanics, it will be the same, the correct frequency. And also you said the force field was tuned for this one. So let's agree that this is correct. But now I'm talking about the transport. So what is the difference between vibration, 1500 wave numbers, treated classically and treated quantum mechanically at room temperature? So do you have a feeling of why the two are completely different?
Sorry, can you repeat the
so essentially we have this frequency, high frequency vibration, which are described at the right frequency with molecular dynamics. And imagine is 1500. So the carbon-carbon stretching, just to imagine this, relevant for transport. They are fine-tuned, they are correct. So now we are at 300 Kelvin. It's also relevant, so two numbers. One is the vibrational frequency, the other is the temperature, 300 Kelvin. So now, what is the problem in treating this vibration classically rather than quantum mechanically? Problem that is not there, to finish, maybe to help you, there is not there if I'm considering low frequency vibration, the 100 wave numbers, 200 wave numbers, all this floppy motion of your polymer.
I'm not sure if I understand the
So,
question.
for example, well, I don't want this, not really quiz, it's more like, you know, that the heat capacity really is much smaller for vibration at high frequency because you cannot populate higher phonons. So in the formula of heat transport, the heat capacity is there. And now in your model, you have a much higher heat capacity because all vibration contributed to the heat capacity, while,
of course.
So is there any way of guessing what is the direction of the error because we are treating also the high frequency mode classically rather than quantum mechanically?
Right, yeah, this is, it's probably an overestimation. I'm asking if in the literature, so even if you haven't done it yourself, have you noticed, is anyone talking about this? Is this a common discussion, or is almost like, okay, you do solid, you use quantum mechanics, you do soft matter, you do MD? I think I can answer this question. Yes, yes, we use the heat capacity to extract the thermal conductivity, and with molecular dynamics, yes. Now this is usually pretty much. This is usually, pretty much the real value when we are operating under the or close to the Debye temperature. I think what you are getting to is I found in the literature a calculation of the Debye temperature of P dot, and I think it's around 315 Kelvin. So yes.
Okay, so it's interesting that you reflected on this as well. And then one thing, very close to the last question, or maybe it's the last, is that you also reconnect with the initial issue with the force field. and to what the old book says about thermal conductivity. So the old books in inorganic, they say, well, I create vibration. This vibration propagates, and in inorganic crystalline solid, they are phonons, so they're long wavelength perturbation of the lattice. They propagate, and they are scattered by impurities or other phonons, so they are really a phonon-phonon interaction. And so something cannot propagate so long because yeah, there will be some disturbance there. So in your backbone, your polymer backbone, where the conductivity is the largest, you have more or less the same phenomenon. On one hand of the backbone is higher temperature, so a larger amplitude motion, and they propagate through the backbone until they reach the other side of the backbone, and so you have transportation of displacement, let's say, from one hand to the other. Now, in the solid state physics, and now it's not very different than the solid state from the chain that you have, because it's a very ordered chain and so on. What limits the transport is the scattering of phonon, which they call it phonon-phonon interaction. And in your case, are the anharmonicity effect. So the fact that your mode is not harmonic and so on. But anharmonicity is one of the things which is not optimized in your force field, because you reach up to the harmonic approximation. You fit the frequency, it's all working fine. You think I believe it. So harmonicity comes from dihedral and van der Waals and on the rest. So what's your feeling? Can we trust that, or maybe do we use this simulation to trust them? So yeah, I like your opinion about this particular element that is not specifically optimizing the force field, which will affect very directly your result.
So I will say something about this from this graph. So, for example, so we have done this fitting, to single out the boundary scattering, right? And we got 2 watts per meter Kelvin. And keep in mind, these are like perfect crystalline structures. And there is actually a paper that was published before mine of a very similar system, but using GAF. And they did the same thing, basically. And they calculated here 61 watts per meter Kelvin for the same system at infinite chain length. So I think that this value speaks. You're right, though, that anharmonicity cannot be taken into account with that kind of functional form. However, having this specific force field is certainly better than just using regular GAF, which is what these previous authors did. Yes, I also forgot to mention during the presentation that they also claimed that by introducing small defects in the crystalline structure, then that they could go from 61 to like less than 1. And so we assume that if we do the same in this case, then we can get also much lower thermal conductivities.
Thank you. Actually, just to clarify, your force field contains an harmonic term because essentially...
I mean, it does contain the torsional terms.
Not only all the torsional,
yes.
but the fact that whenever you have the force field with bond is never fully harmonic, so they're only just implicitly. And so maybe one take-home message from your answer is that in reality, it's thermal conductivity that will tell you if this implicitly present anharmonicity are good enough, and then you are telling me that very likely they are good enough. So I think it's an interesting finding, since we will never be able to really implement this anharmonic term in real case. I think this was the end of my question. I checked the time. It looks more or less how long I wanted to ask question for, and I'll pass this to Jordi.
Thank you.
Okay, thank you. We continue with Dr. Jordi Faraudo.
Thank you. So let me start by expressing my congratulations to you and your supervisor for this excellent work. I mean, you did an excellent research, and it's clearly demonstrated by the publications that you get in top journals. So again, congratulations. And regarding the manuscript and the thesis itself, the writing document, I mean, and the topic, I find it very, very interesting. I have to say that I'm expert in soft matter simulations. So I do molecular dynamics and solvation free energy calculations, these sort of things. But I never worked on semiconductor polymers. So the topic is new for me. The methods are methods in which I'm very familiar with all of them, but the topic is completely out of my expertise, and I find it very, very interesting. And you motivated it very well in the introduction of the thesis. I have also some comments about the document. I will say that you have a few obvious typos that you can easily correct, right? Sometimes you have question marks, typical of LaTeX errors, and
yes.
these sort of things that, you know.
Actually, Dorothea Schoenemann warned me about this, but I didn't have time to.
Yeah.
I haven't printed it, so I can still correct.
Okay. And then one other thing that I miss from the thesis is that I found that there is a lack of general references in some general aspects of the methods. For example, when you explain in many of the methods, when you explain DFT, for example, or in many other cases, you said, okay, you explain the general idea, which, by the way, you explain it very well. But then when you go to the details, you say, okay, these details are out of the scope of this work, which is also okay. But then, I mean, you can provide a reference there. I mean, you have many excellent books on DFT, on whatever, or reviews, and then you can provide an up-to-date reference for the interested reader. Imagine that another student is reading your thesis to start his or her own work, and then it will be useful, right? And okay, these are the general comments. Oh, another one is that I read the thesis and also I read the papers. And normally what I found is that you have more details in the thesis than in the papers, right? You include all the details of the calculations, some trials that you did, some tests, convergence analysis, whatever, in the thesis. But usually you don't include all these details in the papers. But in your case, it's a bit of the opposite, right? I mean, some of the details that I wanted to find were available in the supporting information of the papers, but not in the thesis. For example, the convergence of the density or the temperature in the simulations, you have this data in the advanced functional materials paper, but not in the thesis. So I think it's a good idea to include all this material and even more detail in the thesis. But I mean, that's my opinion, right? Okay, so let me go to the questions. Okay. Let me start with the radial distribution functions that you show many of them in your work. I have a question about all of them. If you can go to any of them in your presentation.
Okay, for example.
Yeah. Well, this was more intensity. I want the radial. Okay, this one, for example. Okay, I mean, when you that's okay, right? The calculation looks okay, but the reason weird thing here is the units, right? I mean, usually we normalize radial distribution functions in a way that for large R, it goes to 1, right? And you describe this normalization in the method section in page 34, yes. But then clearly you are not using this normalization that you describe. Can you tell me why?
Yeah, I don't.
I mean, it's not a fundamental question, right? But it's, as a practitioner in the field, it looks strange to me. And because you're using the same criteria and the definitions that I used, then, I mean, it's strange to see that description not use it in the.
I think when I was writing the Python code for the radial distribution function, and I was trying to normalize, I would get some strange results and didn't understand why. I was expecting one, but didn't. And so I just couldn't seem to solve it. And then I just, left it like that,
Okay.
even though I knew that theoretically.
Yeah.
So that there was some weird bug that I could not.
Okay, so I mean, it's good that you try to write your own code. That's perfect, right? But
Yeah.
in that case, you don't need to reinvent the wheel, because you use a BMD, and in BMD you have an option to calculate these things automatically, right?
Yes, but in this case, I needed to do it custom because so I was calculating the set of particle references was the sulfur atoms, right, in the p dot, but I wouldn't calculate the distance between between a sulfur atom and another sulfur atom in the same polymer chain, and so that
Okay.
wasn't available in any commercial software, and I needed to do it.
Okay. Okay. Also, you can use MD analysis, which is a Python library that you have a lot of these things also implemented. That's also related to another comment that I have here, that I think it's a good policy to share the scripts that you use for the calculations. Because, I mean, I trust that you did the correct thing to calculate the radial distribution function or whatever, but these things are tricky to calculate, right? I mean, everyone is reporting these things, but it's not so easy. And sometimes, as you said, sometimes calculations do strange things, right? And to guarantee reproducibility, and also that,
Upload it on GitHub.
yeah, upload it in GitHub or any other repository, and then you can share it with the community.
Now that you mentioned, I think I solved the normalization thing, but then it was already published.
Okay, and okay, then let's go for the calculation of the crystallinity. If you can go to the definition.
Yes.
Okay. Okay, I have to say that I like this slide very much, and I was missing something like this in the writing report, right? I mean, this scheme that you have in 3D here with the comparison of the crystallinity calculation and the structure. It's very illustrative, and I mean, it helps to understand the thing. So I'm not really sure to fully understand the numbers that are expected to get from this calculation. So if there is no crystallinity, if you have everything random, you will get 0. And if you have something completely aligned, all the chains completely aligned in one direction, you will get 1. Is that correct?
Yes.
Okay.
So actually, the results are not very close to 1. But so, I mean, this is an amorphous material after all, but
Okay, so all the numbers that you have are really small, right? I mean, sometimes I have to say also that sometimes it's difficult to see the numbers in these crystallinity plots that you put in the thesis. At least for me, that I have, I'm not as young as you, and I have more problems in reading. And but in any case, in all the plots, I have the impression that crystallinities are very low, right?
Yeah,
I mean, like, okay. Show no wedge. And okay, in the paper, it's easy to see the graph, but in any case, if you can go to one of the results that you have, the typical ranges of here, for example, that's okay. The typical ranges that you have in crystallinity between the blue regions and the green or white regions are several orders of magnitude, but still well below 1, right?
yes. So yes, these are of course still amorphous materials. And actually, what I did here was restrict the range to highlight the blue spots. So actually, it's a little bit higher than that. But yeah, they are low since it's an amorphous material. So there is only sometimes there is some alignment maybe between 2 or 3 chains, but then it's completely lost. And they are more like a sort of spaghetti sample. And so yeah, the values are low. We'd expect if we applied the same, the same measurement to the crystalline samples, then we would get higher values, of course.
Okay, no, I was very surprised and I was not sure to fully understand. I mean, I'm not familiar with this polymer, so I suppose that your explanation is right,
This
right?
was actually not, it was not about getting a number, since this is a custom just dot product. It doesn't have a real like physical quantifiable meaning, but the main thing was to generate this figure,
Okay.
so that you could see the p dot aggregates.
Okay, no, I mean, I was curious about this particular thing because I used to work with other polymers like cellulose, for example, that they have a very high degree of crystallinity. And compared with that, I mean, it's amazing, right? I mean, this is really amorphous and it's far from a crystal thing, right? But I wanted to be sure that I was really understanding that, right? Okay. By the way, I think that adding more explanation about that in the document will help, right? Like explaining the limiting behavior of this thing, that if you have a crystal, this will tend to 1. If it's completely disordered, it will tend to 0. That helps, right? And then about the simulation protocol, another question that may be related to the fact that I never worked with this particular system. You mentioned that you use, for the structural relaxation, you made simulations for 10 nanoseconds. I found this time very short. I'm used to use much longer simulation times, but of course, this is really system dependent, right? I understand that you take these 10 nanoseconds supported by the time evolution of the density, the convergence of the density.
Yes.
That is shown in the supporting information of a paper, but not in the thesis. And but at the end, density is an average quantity, so it's okay. But how do you know that other quantities that are more local, like for example the crystallinity order or other local things that are not average, are really converged after 10 nanoseconds?
Yeah, I guess you don't really. However, I think I've seen enough literature where this is a average value.
So let's say it's a standard for this polymer in the simulations. Okay. Okay,
Yeah,
maybe,
it
I
can
don't
be a
know.
bit- for P.PSS, it's a lot longer because the annealing cycles take longer. Yes, I would have liked to use 1 femtoseconds, and then it would have been easier to simulate for longer time, but the simulation wasn't stable for with that time step. Apparently, yeah, it would generate all sorts of errors, and the 0.5 was the maximum I could go with.
Okay. So now you are, in fact, answering another question that I had. Why the half femtosecond time step? Okay, it's clear. Right? So it means that the simulation is tricky, right? Because I don't need to go beyond 1 femtosecond in classical molecular dynamics. I mean, if you are running
In fact,
reactive simulations or ab initio, molecular dynamics, a different thing. But yeah.
in fact, yeah, for a while, for a few weeks at the beginning, I really couldn't understand why, because 1 femtosecond always worked like a charm, and then with this system it wasn't working. And LAMMPS doesn't really tell you, oh, you have your time step is too long. It gives you like some weird comments, and you have to figure out what's wrong. So it took me a while, but yeah.
So now I have questions about the calculation of resolvation-free energy. You discuss a little bit the protocol. In fact, you discuss it more in your presentation, that I like it very much, more than in the thesis. I found the discussion in the thesis a bit shorter, and I lacked some scheme or some more explanation than that. I mean, I'm familiar with that method. I use that. But
About
about the calculation of the free energies.
Right.
The free energies from DFT, right? And yeah, you made here some scheme showing which things you calculate really from the DFT configurations and the approximations that you include. Yeah, this one. That's a good scheme. And I think also that more details can be added, at least in the thesis. For the presentation, it's perfect. Because these things, the solvation models have some tricky things, right? I mean, I assume that also you did the DFT calculations using implicit solvent for the calculations of the configurations of the solvent molecules and the proton, right?
Yes, I think SMD.
So it's not, it's a calculation that has some, and then for using these implicit models for the calculation of the configurations, there are also some parameters that you need to provide. This usually depends a lot on the radius of the cavities of the atoms that you use in the model, and that's a tricky thing, at least in my experience.
I think I didn't change anything. Gaussian gives, I forgot to mention I used Gaussian. And it gives you the opportunity to just write the number of the name of the solvent, and there's the parameters that model the solvent are available in the Gaussian documentation.
Yeah, but even in that case, I mean, Gaussian is good in that sense because it's very easy to use, right? But sometimes you have things hidden in that simplicity. And one of the things in Gaussian is that in addition to the details of the solvent, you have to provide some details of the atoms that are going to be solvated, right? You use a radius, a size for the atom that is not a DFT well-defined quantity, right? I mean, it's something that is semi-empirical. And Gaussian by default uses some numbers that you can change, and you can make a selection of different options. And if you try this, it can change a lot, the numbers. Sometimes it's not, so you are lucky, but sometimes it affects a lot. So it's a tricky thing. And I think it's worth to explain it, right? I mean, I'm not saying that you are doing an incorrect thing. I mean, you are right, that what you did is a standard in the field, but it's good to explain that, that you have these tricky things when you explain the method, right? And concerning the results, I was curious about the structures. I mean, you generate the structures with different numbers of solvent molecules around the proton to make these calculations.
This is,
But you are not showing any of them.
You are not sure?
You are not showing the structures, how the molecules are oriented around the proton and how they are oriented between themselves in the first coordination shell. And I'm asking this because with the numbers that you put, you consider up to 7 molecules. And I'm not really sure whether these 7 molecules fit in the first coordination shell, or you're including part of the second coordination shell, or how is this geometry arranged around the proton? Can you give some ideas about that?
Yeah, if I remember correctly, so the solvent is DMSO.
Yeah.
I think there's at least one solvation shell, probably more. What was happening in the structure was that the proton was getting inside in a sort of sandwich between 2 oxygens from 2 different molecules of the solvent. And all the other molecules of the solvent would arrange around this. So proton, solvent, and all around it. I'm sorry, I didn't prepare an image.
I think it's good to put at least some of these images, because then you get an idea of how is this coordination shell and how is the structure that you're calculating the solvation. And considering the results of the solvation free energy, you show several plots of the solvation free energy as a function of temperature, right? If you can go to them.
Yes.
Yeah. Here, for example, in these plots A, B, and C, the free energy is almost independent of temperature. I mean, the slope is very small, right?
Yeah, it's small. Yeah.
So it means that you don't really have entropic effects, right? Because entropy is a derivative of the free energy as a function of temperature. So my question is this realistic, or is a feature of the model that is neglecting some entropy in some way?
So maybe I've been doing this research maybe a little bit too much naively. However, this is basically I copied the method from a paper that I saw in the literature that was done for P dot. And for P dot, the opposite happens. So the delta G becomes more negative at high temperature because there is no proton solvation involved in that reaction. And yeah, what do I want to say? Right, I've been told later after publication by some colleagues that, but Paolo, maybe you are, maybe you neglected the fact that the viscosity of the solvent is changing as a function of the temperature as well. That's why, yeah, so that's a possibility, yes.
Okay, so I have more questions, but I think that I will, yes, I have more time. Okay. Well, I mean, I will just make another one, right? And that's it. About the method for the, so I go back to the beginning, to the method that you use for calculating the thermal conductivity from the relaxation of the temperature. That you use a solution from the thermal transport equation in which the temperature decays in some particular way, and then you feed the relaxation to determine the thermal conductivity, right? You make some comments about this solution, but I mean, again, it will be great to have a reference for that, to see how is the derivation. But my question is that, you know, at the beginning, you have one region with one temperature and another region with another temperature. And then you let the system evolve and equilibrate. But then during the equilibration, you will have a gradient of temperature, right? So it's not just that you will have, I mean, at the beginning, you have part A of the system with temperature 1 and part B of the system with temperature 2. But during the time evolution, you will have a gradient of temperature. So which is not exactly what you have in that solution of the transport equation, right?
Yeah.
Or I'm missing something?
No, you're right. Of course, the temperatures of the two regions do not just, you know, do this, but there is a temperature profile during the equilibration in the system that is much more elaborate. However, we look at the average temperature difference, meaning when we define in lumps those two regions, we are able to just calculate the average temperature of one region and the average temperature of the other region, and just do just look at the difference between those. This works if the system is homogeneous. I mean, if I include like several different polymers and you know, with different concentrations here, different concentration there, then it doesn't work anymore. Because we're talking about two different materials, we're talking about different morphologies even. But when the system is homogeneous, then it works.
Okay, so as long as the thermal conductivity is the same on all the system,
Yes.
this method is correct, right?
Yeah.
Okay, so I don't have more questions. So let me congratulate you again and your supervisor.
Thank you.
Okay, thank you. I want also to join the congratulations to my feeling. after reading the thesis, seeing the presentation, and looking at the articles just in diagonal, yeah, my feeling is that in these years of your PhD, you've learned a lot and you've worked a lot. And that's like my general feeling. And for that, I think everyone deserves a congratulations to you. You reached the end. So that's really good. But after my congratulations, I also have some criticisms. The presentation was, I mean, was fine, was perfect, was what was expected for a presentation, but for the manuscript, I will join Jordi's comments. I'm sorry, but I have the feeling that as if you started writing from the beginning, like with the introduction on DFT, on polymers, then on doping, on molecular dynamics, DFT, and there it's really extended and really useful, especially for me that I'm an experimentalist. I'm familiar with simulations, but I don't do them myself. So everything was really well explained in detail, so you could follow really well. But then you reach the methods that you actually used, and then everything is a bit rushed and short. And then you get to the results and discussion, and it's even rusher and faster the farther you go. So like, let's say like the last chapter, well, not chapter, but section where you explain this last part with the solvation and everything is really rushed. I mean, it's like, okay, that's it. And it's okay. I mean, this is fine. The articles are perfect. The presentation was fine, but it's a bit a pity that to get like this feeling that some more details are missing. As Jordi was saying, that it's surprising that you find more details in the articles than in the thesis, where you have like as much space and length as you want. So that's something that I think could have been done a bit better. Also, I find, as an experimentalist, I find like missing more comparison to experimental results. There are some, but I'm still missing some because I really like more that part, but I'm missing them a bit. But I'm also missing like some references in general. Maybe in my case, not so much the ones that are like really general, but some specific ones. For instance, if you go to slide 48, I don't know if you have the manuscript as well. 48, yeah, this one here. Now that seeing the presentation as here is Lewis pair dopant complexes, there's a 15, there's here a reference, and then you explain this figure. Neither in your presentation nor in the manuscript, I have I still don't know, I'm sorry, but I still don't know if these are experimental results or simulation results. That's one thing, sorry. And the other thing is that this reference here was not in the manuscript. No, neither in the figure caption, not in the text. So I just saw the figure, the comments on the figure, and I really didn't know if it was experimental or simulation and where it was coming from.
Okay, I must have slipped because I'm one of the authors. Yeah, I will certainly then correct it. And about this figure, this is experimental. This was done by Mariano and his postdocs. So
these were like general comments from the manuscript, like things that I think that can be improved. And now we have some questions regarding your calculations. Again, I'm experimentalist, so maybe some of my questions are really naive and everyone knows the answer except me. But for instance, I'm really worried with the hydrogen bonding issue, let's say, because I know that it's not easy to introduce it in a simulation, in a molecular dynamics simulation, as one of the energy, of the potentials. So when I read the first time that you were not including the explanation for the hydrogen bonding, I said, okay, fine. I don't know how good is this approximation for this particular system, but then I continue reading, and when you explain the DFT results, okay, it's with a different molecule, but still, when you explain the DFT results, you claim that this local density approximation, this LDA, doesn't work when there are van der Waals and hydrogen bond interactions, so you don't want to use it. And then when you go to, I think the figures are also here, when you show this straight chain for the polymer, and then you show these very nice pictures with the different type 1 and type 2 interactions or bonding, let's say here, okay? You claim that for type 1, this is hydrogen bonds between these groups, but you're not including the hydrogen bond potential for your calculation. So is this really compatible?
So this was maybe a little bit ambiguous. You're right, because in molecular dynamics, yeah, we cannot observe actual hydrogen bonds. It's not included in the description. Yeah, what I meant, yeah, maybe it's a little bit exaggerated to claim there is a hydrogen bond there, but what I mean is that the red particles there are oxygens, and they're sort of creating a network. If you look like top down within the figure, a network of oxygen, hydrogen, oxygen, hydrogen, oxygen, hydrogen, etc., which does not appear here. And that's the difference.
And this would come like from the Coulombic interaction, or, I mean, how is it that hydrogen and oxygen are getting together like this?
There's both, of course, Coulombic and van der Waals. But yeah, also the distance between these oxygen and hydrogen atoms is compatible with the, I was surprised to see that as well, but it's compatible with the hydrogen bonding.
Okay, so well, you say that you
Sorry.
don't see hydrogen bonding in molecular dynamics. No. It's more that you don't include it already from the beginning.
Yeah, it's not included in the model, right?
Okay.
But it's like the structure is still observed like a similar structure to a hydrogen bond.
Okay, I have another question. This one maybe is a bit silly, but when you use this approach to equilibrium molecular dynamics for the calculation of the thermal conductivity, well, in this method section, you explain that you introduce this delta T, well, this delta T, these two regions at T1 and T2, but then go to the, no, wait, sorry, to the, when you apply this to your actual systems, like your box for PDOT and PSS, or your chain, so that means what? That you're taking half of the box at one temperature and the other half at a different temperature. You're taking two boxes, you're taking half of the chain. I really don't know how you apply this method to your, once you get your box or your chain.
So yeah, once I have the system relaxed, I just take the box and divide it in half. And what's on the left will be on the left half, and what's on the left will be on the right half. For example, with the amorphous system, you will have, well, statistically half of the chains on one side and half of the other. And yeah, it's applied for half of the box.
And doing that, don't you need to take maybe a bigger box, like to be able to be sure you're equilibrating at both sides and they are not too small, let's say, because you're taking half already of a relatively small box because of calculation issues?
No, I mean, well, this is not included, I think, nor in the article, nor in the thesis, but we were asked by the reviewers to provide proof that we had large enough boxes, and this was done. So yes, I believe they are big enough. And although with the nanofibers, they were probably not big enough, and that's why we did the extrapolation to get the actual values. And this was because these nanofibers were their aspect ratio was very much skewed, like they were long along the backbone but limited diameter, let's say. There were some technical problems with the supercomputer, because LAMPS needs to divide the simulation box into mini boxes, and each mini box needs to be with a specific node in the computer. And if you have a very skewed box, then LAMPS doesn't know anymore how to subdivide the box, and then it would give a lot of errors. So we needed to stop and then extrapolate. So yes, if that answers all the questions, maybe did I forget something?
No, it's okay. Now that we're talking about the chains, this is also very like, I don't know, silly question maybe, but when you take your chain and you like, I imagine you build it, but then you let it equilibrate at a specific temperature before introducing these two different temperatures, isn't it? No, you increase the...
First of all, I insert the molecules and they do nothing. And no, sorry. So the system is relaxed, right? And then I define the regions. And then I take the cold region, for example, and I say, okay, now you freeze. Don't move. No forces on you.
Okay,
and then
but
I
my question is...
this one.
My question is for the chains. I mean, because you show these boxes where you have the P dot and the P dot with the PSS, and then you see all these like bent and don't know, curve chains, no, that are not really straight. But then you go into the straight chain, and somehow you let it, I imagine, like evolve a bit before starting your actual calculation with the difference in temperature. This is not a stable state, no? The stable state would be like to be completely bent, as in the previous like chapter, let's say. And now here is completely straight. So this is out of equilibrium. I mean, it's not really a calibrated system. So when you increase the temperature and you let it like this, do you need to like keep the system imposing that you, for instance, cannot have like specific angles to change?
No, apparently it's sort of, so the crystalline system stabilizes itself with the pi interactions. So what I noticed is that, for example, during the replication protocol, for example, there was a specific order of replications that I needed to use in order to generate this sample. So if I did pi first, then it would work, and it would sort of just stabilize itself. And even if I increase the temperature, it would just, wiggle a little bit more, but it wouldn't go out of equilibrium. It would just stay. And then once I had like 2 or 4 chains that were pi stacked, then it was safe to also replicate in the other directions. Otherwise, it would just break. You're right.
Okay, so you build it like one by one and let it, okay.
Yeah.
I also had a question regarding these pi interactions when, and also with like a bit concern with like Jordi was saying about this crystallinity calculation, but also the distribution of radial distribution. If you can show the radial function distribution and the crystallinity, yeah, I think, well, not this one, but well, it doesn't matter. This one is also fine, but the one that you also see, like the one for the crystals, this calculation for the crystallinity, it's a bit weird, and in the sense that it's not that it's not okay to do this calculation, which is, it's perfect, but to call it crystallinity calculation is a bit strange, especially because when you build a crystal, it's not only the fact of that you are stacking something, but you are building also some bonds in there, and here you are only checking the orientation of the molecules and seeing if you have a specific orientation in more in some places than in others, let's say. And also, I find it missing to correlate this distribution of these clusters where the molecules, the chains, seem to be kind of bent in a specific way with your data from the radial function distribution. Because when you are bending these chains, if I'm not mistaken from what you said and I read and what I know, I imagine that it's because of this pi-pi stacking. So at some point, there's kind of a correlation between the amount of pi-pi stacking and the distance that you have here with this crystalline, with the formation of these clusters. So these clusters, if it's like the chains are kind of ordered, this is related with the amount of pi-pi stacking that you are having,
yes,
isn't it?
Yes.
But there's no correlation anywhere in this sense.
Correlation between...
Yeah, somehow, because if this pi-pi, this pi-pi stacking is being a crucial point in conductivity, either, mainly electrical conductivity more than thermal, but if this is really relevant parameter and you want to specifically check it with the distance, yeah, if the clusters you're seeing with your ordering are related to this pi-pi stacking, yeah, if there's a correlation between these two, you can provide a kind of percentage of your sample that has this kind of correlation. To do some extra analysis of your data, seeing if you can find, not just calculating the crystallinity and seeing you have clusters, but trying to get something from there.
So, yeah, we tried to do it, but it just didn't show any correlation. So we didn't include it. It didn't seem interesting. Maybe we were wrong, and just it would have been right maybe to say, yeah, we did this and it's not interesting, but here you are.
Yeah, but when you see these clusters, in these clusters you have some order. What is this order? Is this really the molecules like pi-pi stacking or not? Or is a different kind of orientation of the chains?
This is this is what we expected, that it would be pi-pi, since we defined those vectors to connect carbon to carbon along the backbone. So then if they are really parallel, then they are pi-pi stacked. Yeah, to also answer the other question, that's why I said we called it local crystallinity, but we were afraid this was our, let's say, internal lingo to understand each other, but then we didn't know how else to just to convey it to the community that was maybe more expert than us in this aspect.
Okay, I would like to go to, I think it's like the previous slide or two before this one, where you have not just before, this one here. This figure, now I've seen from this discussion that I'm not the only one that I'm concerned with this figure, but yeah, it kind of worries me a bit. Okay, the issue of the error bars has been already discussed, so I'm not going into it again. Also, the issue that when you comment in the presentation, I'm not sure I read it on the manuscript, but in the presentation you comment that for the bipolaron that you see kind of a maximum for the conductivity, that a trend that it goes like kind of a maximum there for the middle sizes. I really don't see it in the sense that maybe there's a maximum, but that you have such an oscillation in here for all your data in this region that claiming that, I mean, maybe there is, and maybe it has some sense because it contrasts a different thing there, but I wouldn't claim it from this data.
Yeah, I mean, maximum is maybe an exaggerated claim. However, it's clear that it is not monotones.
But yeah, but I mean,
There's
looking
not even
at
a trend.
looking at these oscillations, I mean, it can happen that the point that you have at 18 is also a bit higher, and then you don't have a maximum anymore, but you have a step.
But yeah, anyway, in the undoped case, you have like below 0.1 here and like 150 here, whereas here you have 130, 130. So that's a clearly different.
Yeah, but that's
right?
why I would say that the maximum you can say is that it's relatively flat. Let's say something like that.
Yeah,
This
yeah.
maximum here,
Sort
I
of
don't
as
know, it's a
tab
bit
of-
too it's a bit too much. But yeah, I mean,
Yeah.
looking at these figures and these trends and the uncertainty and all this, I completely agree with Alessandro in the sense that I know more calculations is really costly. I mean, it's not that easy, but yeah, it would help like to extend your uncertainty to see the reproducibility of your results. But for instance, here you talk a lot about trends in this figure, and I see that if you look at the conductivity figure, you have a blue line that is increasing. That's positive trend. I mean, can be claimed. Then you have like something that is more or less flat, maybe for the one that is doped with the with the bipolar ion.
Yeah.
But then at this 18, they get together. But then we don't know what would happen if we were like at 22. I mean, would they continue like with the same trend, and then here we have a crossover in conductivity, and how to explain that? Or from this moment they would like start going flat, I mean together, no? I mean this crossing point and the fact that the two of them are equal at 18, I think it deserves kind of an extra explanation.
Yeah, so I expect the blue line to go further up and the red line to either be constant or go down for the same reason here, like there will be more empty spots in the sample where there is no transport because of the increased rigidity. Also, we didn't think this would be interesting since p-dot chains have been shown to be no longer than 18, 20 units. So we decided to just stop.
Okay. I think that's my last question. At some point, it's in page 45 of the thesis. I think you didn't mention it here, that you do this to like help the dope system with PSS, the p-dot with PSS, that you do these annealing cycles to much higher temperature, like to provide some mobility, and then you go down again. But yeah, I don't know. I can't stop thinking in if you do this like in an experimental, you cannot go up to 1,000 degrees and nothing happens. Just they move a bit, no? Yeah. And yeah, the parallelism is there. So when you use this method to increase so much the temperature. Is it that you increase it? I mean, I would expect if it was like closer, not, of course, not a real system, but closer to a real system, that it's not that just that you are just providing energy for this mobility, but maybe you are changing or breaking bonds when you go this high in temperature. I mean, many things can actually change, not only providing mobility. So I imagine that this annealing has kind of some limitations in what molecules can do when you increase the temperature so much.
So in this kind of molecular dynamics simulation, it's not possible to break the bonds. What is possible is that if I were to like simulate, I don't know, 1 million Kelvin, then yeah, it would generate forces that are so high, then you would get like bond distances of, I don't know, 10 angstrom, and then the calculation of the forces would be like, you have 10 angstrom here, I have to calculate the harmonic term, and it would give like an absurdly high force. And then LAMPS would tell me, look, I cannot go on like this. Here's an error, stop this, I cannot do this. But 1100 Kelvin is still fine. For LAMPS, they can handle.
Okay, that's quite a lot, but still okay. Yeah, my last question, well, not a question, is between a question and a comment. When you select your cutoff radius, the RC, for your simulations, well, I understand that you use a criterion because you have to choose one before you start your simulation.
Yeah.
I imagine that you have a criterion for selecting it based on the size of the chains.
Yeah. So if I remember correctly, it should be 10 or 12 angstrom. Now I'm not quite sure. But yeah, this should be enough to represent like 3 to 4 like clusters of 3 to 4 pi stacked chains. So yeah, that's the criterion. And also, yeah, it's what people use in the literature as well.
You're already counting with the fact that the chains are going to, like, I don't know the name for that, but like to bend, because otherwise, if they wouldn't bend so much, no, like doing these small things, this would be, I mean, that would be too short, maybe too small.
They have enough time to find their own, the conformation that they prefer the most. And when PSS is involved, time is not enough, because PSS is quite long, and also there's like some electrostatic friction and stuff like that. And then it needs more energy, which I provide with annealing with the temperature.
In the thesis, I missed a place where the size of the monomer was stated. Like, I had to check in internet for the size of the monomer to like understand if the distance that you were choosing for the box and for the cutoff, like, I think it's also there, was like, I mean, of course, it was going to be reasonable. That's published and it's your work and it's well done. But like for me to understand if it was okay or not. So yeah, that was missing. I think that with this, I finish my questions. In case that there's a doctor in the room that wants to ask something to the candidate? No? Okay, then thank you, Paulo. We are going to deliberate. So please, if all of you can go out from the room. Thank you.